Yep.
Did you miss me?
I did.
Sir. No one missed you.
All right, guys. Questions over the homework?
Nope. No. I need to get it all done.
Questions over any of the homework assignments?
I mean, this isn't a question, but on my little paper, missing assignments, you put down on my paper.
Okay.
6.5. Put down on my paper.
Yep, you did it. I have it right here. I can double check and make sure I got it put in there in the correct spot.
I'm Rick. His high school like quote. He just put biggest hair roller.
All right, guys. What we're doing today is more solving these exponential and logarithmic equations. All right, guys. Now, there's three kind of main steps with solving these exponential and logarithmic equations. Because if we look at this first one here, 2 to the x equals 7. How we did these on Thursday is we got the bases to be the same. So we would get both of them as 2 to a power. So one side we have 2 to the x. The other, we have 7. So if we try to rewrite it as 2 to a power, well, 2 squared is going to give us 4. Now 2 to the third power is going to give us 8. So there is a decimal or some number between 2 and 3 that's going to give us this power of 7. But we would have to try to approximate it. It would take too long to try to guess and see what decimal number would give us 7. Because we could try 2.5. So what we need to do is get that x out of the exponent, guys. We need to get that x out of the exponent. Now the first main step is to make sure or get the equation to have one term on either side. All right, guys, focus, guys. So the first main step is to get one term on either side. Either be a log on either side, a log on one side, one log term, number on the other, or one number to a power and another number. We just need one term on either side. That's our first main step, and the first main thing we want to do. The second one is to get the variable out of the power, out of the exponent, or log. We want to get the variable out of the exponent or exponents and out of the log or logs. We need to get it out of both so that we can solve this. Now for this here, 2 to the x, we need to get that x out of the power, out of that exponent. And to do it, we're going to use logs. And the way we do this is we're going to apply log to both sides of the equation. Specifically, log base 2. For this equation, we're going to use log base 2. All right, guys. We're going to apply log base 2 to both sides to get the variable out of the exponent. Now, there's a specific reason we're using log base 2, and I will explain that fully here in a minute. Questions on this so far? All right, guys.
Turn around.
Now, if we look at this here, one of our properties of logarithms is that if we have an exponent inside the log, we can move it to the front, our power property. So our power property says we can take the exponent and move it to the front. And the reason this is helpful is now we do not have the exponent, that variable x, as a power, as an exponent. So we're able to get the second step done. Now we just need to solve the equation. We just need to solve for that variable. Sometimes we have to get it by itself. We need to get it on the same side, but we need to solve for x. You guys? Guys? So, guys? Now, on the left side, we have log base 2 of 2. There's a specific reason I chose log base 2. Now, if we calculate log base 2 of 2, the value for it is 1. So with this here, it means that this log base 2 of 2 is 1, telling us that the left-hand side is x times 1, or just x. Now, the reason we chose 2 for this here, and it's going based off of this here. We saw this earlier, log base b of b. If the base and what's inside the log are the same number, it reduces to 1. So log base b of b is 1. Log base b of b is 1, so it reduces out. That's why we chose log base 2, is to get this log base 2 or have log base 2 of 2, which simplifies to 1. So now we just need to solve for x. Well, x is already by itself. So we have solved for it. The only thing we have to do after this is to find the approximate value of log base 2 of, guys. So the approximate value of log base 2 of 7 is 2.807354922, or approximately 2.807. And that's it. On the test and on the homework, if you want to give me both, I will take both. But at least I do want that x is equal to log base 2 of 7. We have one more. One more after this. Chapter 6 and 5. Next week. Yes. Yes. Questions on how we solve this? Guys, questions on this? You ready for the next one? All right, guys, 3 to the x equals 8. So we do have one term on either side. We have 3 to the x on one, 8 to the other. So to get the variable out of the exponent, we're going to apply log to both sides. And specifically, we're going to apply log base 3. Now, when we start getting variables in both exponents, we could just use log or natural log, or we can use log of one of the bases to make it a little bit easier. But we do need to apply log base 3 to both sides. And the reason we do that is because our power property says we can take that exponent and move it to the front, telling us that we have log base 3 of 3 is equal to log base 3 of 8. Questions on this so far? Log base 3 of 3 is going to be what? 1. So that just tells us the left side is just x. and x is equal to log base 3 of 8. And that's it. Now, so far we've seen to get the approximation, we can plug it into the graphing calculator, find log base and do it that way. The other way is change of base. Because log base 3 of 8 written in the change of base would be log of 8 over log of 3. And we can get the yellow calculator and do log of 8 divided by log of 3. And we get 1.8927 or 1.893. All right, guys. Questions on this here? Yes. Questions on anything we've done so far? All right. We ready to look at the next one? Seven to the 9x equals 15. We do have one term on either side, so we can apply logs to get the variable out of the exponent. Because if we start with an exponential, we're going to have to use logarithms to solve it. If we start with a logarithm, to get the variable out of a log, we have to use exponents. And for this here, the base of the log would be 7. Now we can move the 9x to the front, telling us that we have 9x times log base 7 of 7 equals log base 7 of 15. Now our log base 7 of 7 is going to reduce to 1, leaving us with just 9x. Now, on all the ones we've done up to this point, it's just been x equals and we were done. But for this one here, x is not by itself. What do we need to do to get x by itself? By 5. And that's it, because we got x by itself, so it's solved. Now, for the most part on the test, this is as far as I'll ask you to take it. If you want to give the decimal approximation, you can. But I'm not going to make you give me the decimal approximation. Because, again, it asks us to solve. We solve. The only thing going from this to decimal approximation is just plugging it in a calculator. And putting that or having that as part of the graded item is not so much you're testing your ability to solve it, testing your ability to put it in a calculator. We solved it. Questions on this here? And even on the homework, this is as far as you got to give it. I'm not, if you give me the decimal approximation, that's great, but I do want to at least see this. Questions on this so far? 5 to the 3x plus 7 equals 311. So the first thing we're going to need to do is apply a log to both sides. Let's cool it with the rubber bands. Now, what would our base for these logs be? 5. On the left-hand side, the 3x plus 7 is going to come to the front. But our log base 5 of 5 is going to be what? So really we have what? Here it is. Because we could put log base 5 of 5 here if we want. but it's going to cancel out. So we can write it and then eliminate it if we want, but here, because the log base 5 of 5 reduces to 1, it simplifies out. We don't necessarily have to write it. Now with these logarithms, log base 5 of 311, we could see if we can simplify it. Log base 5 of 311, it's an irrational number. These numbers that come out of the logarithms, for the most part, are irrational. There's non-repeating, non-terminating decimals. So for us here, we're going to leave it as log base 5 of 311. Now, sometimes they will reduce nicely, because if we took log base 5 of 125, it reduces to 3. Replacing that with what it equals is fine, because it gives us a nice number. Now we need to solve for x. What can we do first? Minus 7. Leaving us with 3x on the left-hand side, because our 7 minus 7 is 0. On the right-hand side, it is going to be very tempting to want to subtract that 7 and 311. We can't, because the 311 is inside that logarithm. The 7 is on the outside. So we can't actually subtract those two. The only way we would be able to subtract our log base 5 of 311 and the 7 is if we get the decimal approximation of that log first. And what do we have to do last? Divide by 3. Telling us that x is log base 5 of 311 minus 7 over 3. And that's it. Because we can plug it into the calculator at this point, get the decimal approximation, but that's it. That's as far as you have to take it. Now the nice thing with the exponents, or the variable starting at an exponent, that number can be positive, it can be negative, it can be fractional, it can be 0, it can be any number we want, because we can put any number in an exponent. Questions on this here? Do we need to see another example of one of these? Or do we feel comfortable with these? Okay.
Well, ones of us who aren't trying to sleep.
What do you mean?
All right, guys. Let's look at this one here. This one looks a little different. Yes? We have e instead of a base number, but it's still going to work the same. Do we have one term on either side? No. We do have 13 on one side, but our left-hand side, we have the minus 7 and the 4e to the negative 0.3x. So before we can apply logs or do anything to this solving-wise, we need to get that e, that base to a power, that variable, by itself, at that one term. So the first thing we can do is add 7. So on the left-hand side, our negative 7 plus 7 will simplify out, leaving us with 4e to the negative 0.3x equals 20. What else can we do? What else is with e? We have that 4 in front, yes? Because if I divide this by 4, the 4 and 4 will cancel, telling me e to the 0.3x is equal to e to the negative 0.3x is equal to 5. Now we do have one term and one term. To get a variable out of the exponent, we're going to have to apply a log to it. And we want the base and what's inside to be the same. So what logarithm's base was e?
Natural log.
Natural log. So for this one here, we're going to apply the natural log to both sides. And just like before, we can move the exponent to the front. Giving us the natural log of e, don't know why I put x, e, is being multiplied by our negative 0.3x, excuse me, and that's equal to the natural log of 5. Well, what is the natural log of e? 1. Natural log of e is 1. So since the natural log of e is 1, that really leaves us with negative 0.3x equals the natural log of 5. There it is. What do we need to do next to get x by itself? Divide by negative 0.3. Minus x is equal to the natural log of 5 divided by negative 0.3. Questions on this here? Questions on this problem here? Now we could take the decimal approximation of this too. The natural log of 5 over negative 0.3 is negative 5.365. All right, guys, focus. Questions on this here? And again, just like with our logs, the x equals the natural log of 5 over negative 0.3. That's our answer. You don't have to give the decimal approximation. I do want the logarithmic or exponential. Logarithmic mainly. When we start getting exponential, most of those, it's going to simplify nicely. And we'll see that here in a minute. Are questions on this here? Yes. There goes. We ready for the next one? E, 3e to the x minus 4 equals 8. Since there's not one term on both sides, we can add 4 to both sides. Telling us that 3e to the x is equal to 12. Then what can we do next? We can, but I would divide by 3 first, giving us e to the x is equal to 4. Because we could have the natural log of 3e to the x, but we'd have to split those two apart before we can do anything else. All right, guys. At this point, we can apply the natural log to both sides. So we get x times the natural log of e equals the natural log of 4. Well, the natural log of e is 1, so we're just left with x. Since x is by itself, we are done. All right, guys, focus in. We ready for the next one? All right, guys, focus, focus.
I literally lost it.
So, is there one term, guys? Is there one term on either side? Yeah. So this time we can just apply the natural log to both sides. On the left-hand side, the 4x minus 3 will come out of the exponent and leave us with 4x minus 3 times the natural log of e. But the natural log of e is 1. Let's focus. 4x minus 3 times 1 is 4x minus 3. Now we just need to solve for the value of x. So the first thing we can do is add 3 to both sides, telling us 4x is equal to the natural log of 19 plus 3. And last but not least, divide both sides by 4, telling us x is equal to the natural log of 19 plus 3 divided by 4. Questions on this here? Are you ready for the next one?
Yes.
Guys, focus in.
Yeah.
Sorry, yeah.
All right, guys, let's look at this one here. So this one here tells us that log base 2 of 5x minus 17 is equal to 3. Now, one of the other properties that we had with logarithms is that b to the log base b of x, when the base of the logarithm and the base we put it to are the same, they simplify and leave what's inside the log. So for this here, our log base 2 of 5x minus 17. If we put this logarithm to the base of 2, we get 2 to the log base 2. That there, this here, will simplify out, leaving us with 5x minus 17. When the base and what's inside, or the base and the base of the log are the same, those simplify out. And the main reason this works is because our logarithms and our exponential equations are inverses of each other. They undo each other. But what we do to one side, we have to do to the other side. So we have to put that 3 to the base of 2, so 2 to the third. Now, will 2 to the third reduce nicely? 2 to the third power is 8. That's why these logarithms, when we're going from a logarithm using exponentials to solve it, we get nicer numbers because 2 to the third will reduce nicely. As long as it's not fractions or decimals, there's a good chance it will reduce nicely. Now we just have to solve for x. And for us here, the first thing we can do is add 17 to both sides. Telling us 5x is equal to?
Does x end up equal to 5?
Yes. Divide by 5. So x is 5. Questions on this here? Now, logarithms we do have to be careful with, because we cannot have a value of x make any of the expressions in the logarithm, so here 5x minus 17, be 0 or negative. Because if a value of x makes that 0 or negative, it is an extraneous solution, it doesn't work. We cannot have a number inside the log, guys, be 0 or negative. And the reason for that is because log base b of x equals y if and only if b to the y is equal to x is what we have. So if we said x was 0, what we're saying is that b, whatever the base is to the y, is going to equal 0. And this doesn't work, because if y is positive, any positive number, well, b to a positive number is just going to get bigger and bigger. We've seen that in some of the equations. Putting 2 to any power You're just going to make it bigger. It's not going to make it be 0. Well, the other option is that y is 0. Well, b, any base to the 0 power is 1. It reduces to 1. So that doesn't work. And the other option is that whatever the value of y is could be negative. We have a negative version of it. But our properties of exponent says I can change the sign of the exponent from positive to negative or negative to positive by moving it from the top of the fraction to the bottom or bottom to the top, which is just 1 over b to the y. Well, in the positive case, we said that that number is just going to get big, which just means the bottom of the fraction is going to get bigger, and it's going to approach 0. It's never going to equal 0, but it will approach it. It will get infinitesimally close to it, but will never actually be 0. Because the only way for a fraction to be 0 is if the numerator is 0. Well, here the numerator is stuck at 1. There's no way for this to be 0. So this does not work. We cannot have 0 inside the log. But if you also notice with this here, in all 3 cases, the numbers were positive. They were never negative. We can't have a 0 or negative inside the logarithm. So if any value of x would make 5x minus 17 be 0 or negative, we have to throw that solution out. But 5 works just fine. Because if we check this here, log base 2 of 5 times 5 minus 17 equals 3. Well, 5 times 5 is 25. 25 minus 17 is 8. And log base 2 of 8 is indeed 3. Log base 2 of 8 is 3. So that works. Questions on this here? All right. Log base 3 of 10 to the x, or log base 3 of 10x minus 9 equals 4. What would we do first to get the variable out of the log? Put both sides to the base of 3. And we can start with this here because also we do have one term on either side. Log's on one side, 4 is on the other. And again, our log 3 to the log base 3 is going to simplify out, leaving us with 10x minus 9 on the left-hand side. 3 to the 4th power, 3 to the 4th. Is that going to reduce nicely? Yeah, 3 to the 4th is 81. 3 times 3 is 9. 9 times 9, 81. All right, what do we need to do next to solve for x? Add 9 to both sides. Telling 10x is equal to, and then
Bingo. Great.
and that's it. If we wanted to check it, we could plug it back in. We could use the calculator, guys. Log base 3 of 10 times 9 minus 9 is indeed 4. Questions on this here? Guys?
Is this one gonna be
It was our get our way car.
So the base that we would use for this here would be all right, guys. Guys. So on the left-hand side, we have x minus 6. On the right-hand side, we have 2 to the 5th. 2 to the 5th is, because we're multiplying 2 by itself, how many times? 5 times. And lastly, we would all right, guys.